click it, make sure that it is started. Okay, there we go. I can see the green light. You guys cannot see it, but it's green right now, which means we are streaming at 10 frames per second, and it's using about 6% of CPU time, just for the transcoding and uploading of the stream. So it's kind of nice to have those kind of statistics available. All right, so we'll start with a function that all of you should have known already from cisp310, and then we'll go from there. The function that I'm talking about is string copy. Okay, so this is string copy. We can do either one. Okay, we can do string copy or we can do string and copy. Either one is fine with me. So string copy doesn't do anything too tricky. All it does is all you have to do as a caller is you have to supply a source, which is the string that you're copying from, and you have to specify a destination, which is the array of characters that you're copying to. So do we all understand what is string copy? Because this should be a function that was discussed in cisp360. Is that assumption okay? Okay, I'm only seeing people nodding, so I'm going to assume that we know what this function is. So what we'll do, okay, based on my experience with the Tuesday-Thursday class, is I don't have enough time to talk about the iterative solution as well as the non-iterative solution, which is the recursive one. So I'm going to start off with just the recursive one for this class, because otherwise I won't have enough time to talk about the recursive solution. All right, so we'll go ahead, okay, to talk about that function first. So we'll also look into the function and examine what it is supposed to return, because it does have a return value in case you do not know. So the return value of string and copy is really just a pointer to the destination string itself. So it doesn't seem to be very useful, right? I mean, parameters that you pass to the function, and it returns the parameter itself back to you. It's like, why do we do that? Well, this is so that we can stack function calls. So you can have a string and copy, and the return value of string and copy is used by another string function, and the return value of that string function is used by another string function. So this way you can basically nest function calls to string copy and functions like that, so that you don't have to separate those operations into individual statements. So there is a function, there's a reason why it returns the destination as an argument, as a return value. It returns the parameter as a return value. Okay, so given all of that, okay, we'll go to this open window here, and we'll write out the C code first. So the C code is going to be about the same as what you would think it is. Okay, so here's the destination and const char source. Okay, the const is not really important in the implementation of assembly code, because const as a word, as a keyword, is telling the C compiler to make sure that we are not changing anything that source is pointing to. And the compiler has to enforce that. But since we are translating into assembly code, and you can't really enforce that in assembly code, so the word const here really does not impact how we are going to implement the subroutine. So remember, we are talking about recursive here. So that means the first question we have to ask is, when do we stop the recursion? In other words, in what condition I can do one little thing and we say, we're done. Okay, so we have the conditional statement of some sort. And at the end of all of this, we have to say return destination, because that's what string copy is supposed to do. So we have a basic structure of the code. So let's just say that this condition here is the condition to end the recursion. In other words, this is the base case. Okay, this is the case where we do not need to call string copy again. So I'm going to go a little bit further in terms of converting logic into a recursive version. When you convert an algorithm into a recursive version, what you're trying to do is to look at a problem that is of size n, okay, a bigger one, and you're trying to break it down into a solution that consists of a small step that you can express and also, a subproblem that has the same nature as the original problem, except it is smaller than n. Okay, are we okay with that, discussion, with that concept? Okay, so that's generally speaking, how you convert something into a recursive solution. So right now we have to first think about, when do we stop? Okay, under what condition can we do one little simple operation and we're done with it? Okay, so that's the first question. What do you think? Yep. Okay, so instead of saying when you reach the null terminator, maybe we can rephrase it and say, what if source is pointing to a null char, which is the terminator already? Then we just copy that one single character, and right? Okay. So that means the way we express the condition is when source, okay, it depends on the polarity, okay, you can express it either way. But when source is pointing to something that is not null, okay, then we have to, don't copy this, okay, I'm just going to write it in comments first because I'm restructuring the logic in just a little bit, okay. So in this case, we have to copy and then, string copy the rest of the source string. Does that make any sense? So I will copy one single character. I will copy whatever source is pointing to whatever destination is pointing to. But that's just one character. What about the rest of the string? I will call string copy again to handle the rest. But with both of the pointers incremented. So I'm going to use dest plus 1 and source plus 1 as the arguments. Okay? Okay. What about the else case? What if the condition is false? What if star or asterisk src is false? Well, that means source is already pointing at a null character, which is a null string. So what do I need to do to copy a null string? I just have to copy whatever source is pointing to whatever destination is pointing to, and I'm done. Does that make sense? Okay. So in this case, I just copy, but no, do not call string copy again because we're done. We're given an empty string, copy the null terminator, and you're all done. Is that okay? But the reason why I'm not giving you the actual code right now is because, hey, I look at both of these cases. In both cases, I need to copy one character, which is whatever destination is pointing, whatever source is pointing to needs to be copied to whatever destination is pointing to. Have to of whether source is pointing to a null or not. So I might as well put it outside of the conditional statement because this is something I have to do anyway. So I'm just going to put it over here. Whatever destination is pointing to is going to get whatever source is pointing to. I move it outside because I have to do it. So over here, I don't have to copy anymore, but I do have to string copy the rest of the string. So that means I now have to call string copy. But this time when I call, the destination is going to be destination plus 1. The source is going to be source plus 1. Because whatever source is pointing at is already copied. And the location that destination is pointing to is already having the character that I just copied to. So the string copy that I need to call is now advancing the pointer by 1, both in terms of the source and the destination. Are we doing good so far? Okay. But that also means in this case, the copying is already done, and we do not call string copy again. That means I got nothing to do here. So that means I can also simplify the conditional statement because the else branch has nothing to do. So we just remove the else branch altogether. Get rid of it. So this is now the non-recursive, this is the recursive version of string copy. Are we doing okay so far? Just in terms of the C code? Okay. So if you want to be convinced that this will get the job done, you can actually compile this code and test whether it can properly copy a string to another string. Okay, I'm just going to say that yes, it is going to get a job done, and we'll focus on the assembly implementation in today's lecture. Are we doing okay so far? Yes? Okay. So what do we do when we convert this particular subroutine into assembly? So that's the next step. So I'm gonna use the other window to do this. Okay. So we have string copy as a label in assembly language because it is defining the entry point of the subroutine. So at the entry point, okay, now this one does not make use of any local variables. So we can use another example to illustrate how local variables are used, but this one does not. So by the time we get to the entry point, how many people have done that experiment that was suggested in the lab, which is to put a halt instruction right at the entry point of swap and examine the stack at that time? Okay, so you did it. Okay, so if you have not done it, you should do it. Okay, because you would get a sense of what is on the stack at the time. So I'm going to comment here, okay, at the entry point of string copy, assuming the caller is doing everything properly, then we'll have source here, we'll have destination here in terms of memory location, and then we'll also have return address here. But the stack pointer will be pointing at the return address because by convention, the caller has to push all the arguments first, pushing the last argument first, which is source, and pushing the first argument last, which is destination, and then the caller has to push the return address, and then it has an unconditional branch to string copy. So at the entry point of string copy, this is what we are expecting to be on the stack. Now, if things do not look like this on the stack, it is not the fault of the subroutine. Okay, it is the fault of the caller. So you can assume the caller is doing everything correctly, so the stack looks like this when you try to code the subroutine. All right. So if this is the case, okay, I'm going to use a label to define the offset to each item on the stack from where the stack pointer is pointing to. So to understand the offset, you can probably see this as SP plus 0, okay, because it is exactly at the location that register D is pointing to. This one is going to be SP plus 1 because it is 1 byte above where the stack pointer is pointing to, and this one is SP plus 2 because it is 2 bytes above where the stack pointer is pointing to. Is that making any sense? Okay, all right. So instead of having to mentally keep track of where source is, where destination is, and whatnot, I'm going to define some labels. So the way I define the labels is return address is defined to be 0 because it is 0 bytes away from where the stack pointer is pointing to. Then we can define destination to be return address 1 plus because it is 1 byte above where the return address is on the stack. And then source is going to be dest 1 plus because it is 1 byte above where the destination is. So I'm making everything relative to each other. So this way, if I need to add something or delete something, it's an easier change. Are we still doing okay so far? So from the assembler perspective, all this has done is to say every time the assembler sees return address, it's going to be just 0. Okay, that's the assembler's understanding of that particular word, return address. Every time the assembler sees destination, it says, oh, it is defined to be 0, 1 plus, which is just 1. And every time it sees source, it's going to be 1, 1 plus, which is really just 2. But this allows me to refer to symbolic instead of constantly having to remember where things are on the stack. I only have to do it once, and then for the rest of this subroutine, I don't have to think about the positioning of the arguments anymore. Are we good so far? So that's the advantage of using symbolic names to define the offsets. All right, so we are now ready to implement the first line here. The first line here requires us to to calculate what source is pointing to. Okay, so the first thing, wrong window. So the first thing we need to do is to find out where do we find source as a parameter. So to do that, we do a LDI A, okay, or B or C, okay, it doesn't really matter which register in this case. So you can use any one of the 3 registers, anything other than D is fine. And I'm going to use source, okay. So what this is going to do is A will now equal to, source is 2, right? So A is 2 at this point, which is not the address of the parameter source. It is really just the offset from where the stack pointer points to. Does everybody understand why it is just 2? What the 2 is referring to? Yes? Okay. So the next thing we need to do is to add the stack pointer to register A. So what is register A at this point? It's SP plus 2. But we also know that as the address of source. Is that okay? So register A is not source. It is the address of source. It is the address of a parameter. When you look at the C code, we really don't, we should not stop here because we need to refer to what it points to. Okay. So we need to do LD instruction, LDA A. So once you dereference, okay, so let's look at this, okay. We are looking at this, right, because A was this, and LD is actually just doing a dereference. What is the other way to say this? Okay, let me just say it out loud, okay. How do we say the dereference of the address of source? Just source, right, exactly. And then you look at this, okay, you look at source and go like, is that what we need on line 3 of the C code? Not exactly, okay, because we need what it is pointing to. So what you need to do is to do another one. Because now A is going to be whatever source is pointing to. That's our right-hand side of the assignment. Are we good so far? How do we get to the left-hand side? Look at the left-hand side on line 3 in the C code. Looks almost exactly the same as the right-hand side, right? So that means we can now, don't use A again, okay? Because what is in A already at this point is the right-hand side of the assignment. We kind of want to keep that around if we can, and we can. So we can use register B, we can use register C. You got a choice here. Destination, so at this point B is 1, which is not the address of the parameter. It is the displacement from where the stack pointer points to compared to the address of destination as a parameter. But that's okay, we can fix that. Okay, once we add the stack pointer to it, B now becomes stack pointer plus 1, which we also know as the destination's address. Or destination as a parameter. Okay, it is the address of destination as a parameter. Okay, not quite what we want because we need to know where destination is pointing to, which means we have to get to the value of destination itself. So we need an LD instruction. Oh, I chose the wrong register here because we're using register B. So one dereference will get us to just destination. Just like before, this is the dereference of the address of destination, which is just known as destination in short. Are we good? Kind of the same thing? But we don't want to do another LD because what are we going to do with destination as the parameter? We want to store to wherever destination is pointing to. So we do need a dereference. We're not going to dereference and read. We're going to dereference and write this time and overwrite. So we need a store instruction this time. So we're going to store to whatever B is pointing to because B is destination. So whatever B is pointing to is also whatever destination is pointing to, which is the left-hand side of the assignment in C that we are trying to implement. The right-hand side is already done in register A. So that store instruction is going to accomplish dest equals to source. Are we doing okay so far? Okay. Okay, now that is done, let's move on. Okay, so when we move on, we are now on to line 4 of the C code. If you don't want to make any assumptions of what register, which register has which value, you can go ahead and recompute and redo line 9 to line 12 if you want to. But I recognize that line 12 has register A storing whatever the source is pointing to, And on line 4 of the C code, that is what I need in order to determine should I go to the then branch or should I get out of the conditional statement. So I'm just going to skip, redoing everything. And I'm just going to say, oh, we already have register A having whatever source is pointing to. Let's just check it and see whether it's 0 or not. And that can be done by compare, but I'm lazy. I'm just going to use this trick. So this trick should be not new to you anymore, because we have used this trick quite a few times already in one of the labs and also in the exam. Okay, so this is not a new trick, because with any type of operation that goes through the ALU, as long as it is not increment and decrement, the flags, the Z flag and the sign flag, are always influenced by the operation. So when you end A with A, okay, you end up with just A. So it doesn't really change register A in any way. On the other hand, it does affect the Z flag and also the sign flag. I don't really care about the sign flag. I don't need to know whether it's negative or not. I just need to know whether it's 0 or not. So I can pay attention to the Z flag right after this. Okay? And the only way to pay attention to the Z flag is JZI. Okay? We don't have an instruction that says, well, if the Z flag is cleared, go to this place. We don't have an opcode to do that, because it can be implemented using multiple instructions. So in the spirit of implementing a RISC architecture, we don't have something that says if the Z flag is a 0, go someplace. Okay, we only have this that says if the Z flag is a 1, go someplace, which is fine, especially in this case, because if whatever source is pointing to is null, I just get out of the conditional statement. Okay, so I just go to an endif label. The endif label is going to be here. And if we do not go for that branch, now it means A is non-null. Now, if A is non-null, that means whatever source is pointing to is also non-null, which means now we have to go for this recursive call. Is that okay? Are we still doing okay? All right. So how do we implement that recursive call? Well, whether it's recursive or not does not even matter. Okay? We just focus on the mechanism of pushing arguments on the stack, pushing the return address on the stack, jump to the subroutine that we are calling. And when it does return, we want to clean up the stack. We want to clean up for those 2 arguments that we push on the stack.
So we have a call at this point that would be identical to the call in whatever function is calling this the first
It would, it's not identical in terms of the arguments, but it is identical in terms of how you use the stack. In terms of structure and how we use the stack, it will be identical, yes. Okay, so what do? We look at the arguments. We push the arguments first, and we have to push the last argument first. Okay, so that's going to be source plus 1. Okay, so right now I'm going to go like, well, we did not save source earlier. I could go back and change that. Okay, in other words, when A is source, I could do a CPR and kind of put it into another register. But I'm not going to do that, okay? So we can just go ahead and redo the calculation. So it's going to be a little bit repetitive. LDI A with source, add AD, and LD A. Okay, so at this point, A is source. But it is not source that I need to push. It is source plus 1 that I need to push. Well, that's easy. We just increment A. So A is now source plus 1. And we decrement D, STDA. That's how we push source plus 1. Is that okay? So I'm not going to give you all the intermediate comments. So if you want to do this, it is up to you to add the intermediate comments. Because from here to here, it's the same stuff that we did over here. So the only new stuff that we are doing is increment A and decrement D. So it should be pretty clear by now what those instructions are doing in the context of this code. Okay, so we got source plus 1 pushed at this point. The next thing we need to do is to push dest plus 1. But this time is a little bit tricky, because instead of just loading dest, we have to load dest 1 plus. Okay, now you ask, why is that? If you look at the stack, okay, let's re-examine what is on the stack right now at this point. Okay, we'll comment right here and say, okay, what is on the stack as far as the subroutine is concerned. We still have source, being on the stack. Dest is right under that. The return address right below that. And guess what? We got one more thing on the stack right now, which is source plus 1. We just pushed that on the stack, right? And where is the stack pointer pointing to? The stack pointer is pointing to the very last thing that we push on the stack, which is source plus 1. So the offset to the return address, destination, and source, they are now off by 1 compared to how I defined the labels. Is that making any sense? Yes? Okay. So that is also the reason why we have to load dest1 plus into A and not just dest, because that 1 plus is accounting for the argument, the one argument that is already pushed on the stack. Question? Yep.
Yeah, that wouldn't physically put it between source and dest, right?
Huh?
That's just a name, like to keep in mind where source plus 1 is at, right? It's just a label.
What is a label?
The source plus 1, it's not physically putting it between source and destination.
It is doing the actual calculation. So the constant that we're putting into register A is, dest, which is what? Dest is 1. It's 1 plus 1. It is 2. It's loading a 2 into register A.
Oh, okay.
I mean, this is why we have a postfix notation, is so that we can do computations based on label names and constants and whatnot. Okay. When we get to the assembler, we can actually see what constant, the LDI instruction is loading, and it will be clear at that point. Okay. Okay, so after this, we still have to do the add AD because, even at this point, register A is still only a displacement from where the stack pointer points to the thing that we want to access. So you got to, do the add AD, and then we have the LDAA again, because we are not trying to push the address of destination. We're trying to push destination plus 1. So we need to get to destination first. And then we increment it because we are not pushing destination, but destination plus 1. So the increment is dealing with the plus 1. And after all of this, we can now do the actual push, reserve 1 byte on the stack, store to that 1 byte that we just reserved, register A, which is destination plus 1 at this point. So this is accomplishing push destination plus 1. Are we doing okay? All right. So now we got both arguments pushed. It is time to push the return address. Pushing the return address, using this way is fairly kind of template based. So we just load A with 1.5 plus, which is 5 bytes from the beginning of the LDI instruction. I made the same mistake yesterday, and it kind of messed up the program. So it's LDI A and then 5 plus, and then we do a store. This is actually just pushing the return address. After that, we can do a JMPI to the subroutine that we're calling, which is string copy this time. And that turns out to be the very same subroutine that I'm in, right? But why is it any special? It is not special in any way, okay? Yep.
Could you quickly remind me what the .5 plus means?
It's the address of the LDI instruction plus 5. So this is loading the address of the LDI instruction plus 5. All right, so when we do get back, there are 2 things we need to do, because we need to increment the stack pointer twice, because we have 2 arguments that are still sitting on the stack. They should not be there anymore because the subroutine call is done. So this will clean up the stack. So this will conclude the end of the conditional statement. We only got the then branch in this case. So after and if, we still have to return destination itself. So we can kind of do that all over again. Load A with destination. This time we don't need a 1 plus or even 2 plus, because the stack is once again balanced. In other words, the stack pointer is going back to where it was at the entry point of the entire subroutine. So the label is correctly telling me the offset to destination compared to where the stack pointer is pointing to. So we do this, and then we say add AD, so that register A is in fact the parameter destination. That's all we need to do. Well, hold on, not yet. Register A has the address of destination right now, but we are returning the value of destination. So we do need one load instruction because we need to convert the address of destination into destination. So now that concludes the return statement. Okay, I'm going to comment here. This is basically what is implementing return destination. It's specifying the value to return. And after all of this, we can now properly return to the caller. And to return to the caller, we do a LD. We cannot use register A because the register A is used to specify the return value. So we can use register B or register C for this purpose. This is for retrieving the return address. And then we do a increment D because by convention, it is the subroutine that has to deallocate the return address from the stack. And then we do a JMPB to continue execution in the caller, which can possibly be string copy itself, but I don't care. As a subroutine from this perspective, I just go by the return address. Whatever return address is on the stack, I'm going to use it to go back to where I came from. Are we doing okay so far with this? Okay. Cool. So I claim this code works, okay? But does it actually work? We don't know yet. So what we'll do is we're going to test it out, okay? In other words, we're going to have to write a main in C first, and then we'll convert that into assembly code, and then we'll test the code and see whether it works or not. So we have int main, and I'm going to use a local variable as a string. So const char name, okay, is an array, and it is going to be initialized with TAK and a null character. So this is how you can define an array of characters, and you spell out the individual characters in the string. Okay, this is the long way of saying double quote TAK and double quote. But I'm going to use the long way because there's no easy way to implement the short form in assembly code. So I'm going to have to do it in the long way in C code as well. And I will need another array, okay? So I'm going to have another array that is not const because I'm copying into this destination. And we'll say, applicant, okay? Whatever it is. We'll reserve like a whole bunch of bytes for this in C, like 32 bytes if I want to. And then in the C code here, the only thing I'm going to do is to say string copy. The destination is applicant, and the source is name. And that's all we need to do in main to see if the subroutine works or not. So on this side, you can actually compile this code and see if it works. But on the other side, we have to implement main. So if I want to run this code in the command line version of LogicSim, I need a no op to begin with. And the no op doesn't really hurt if you want to run it inside the GUI. So it's just a good idea to start everything with a no op. LDID with 0 is not 100% needed, but it's good to remind ourselves that we do have to initialize the stack pointer first. And this is the actual starting point of main because the other two instructions really are not a part of main as a subroutine. Now we know that main has to end with a halt instruction because we have to quote unquote return 0, but there's nothing to return to. There's no operating system behind the program that we're going to run on the toy processor. So it's just a halt to basically say, yep, we're all done. So now we have to do the allocation, okay? So do you guys want to do it the long way or the short way? Long way.
Sure.
Long.
I'm hearing a lot of people say long.
Yeah, I heard that too. If you check the recording of the video, there will be a lot of long. Yep. So we'll do the long way. So the long way says, we have to allocate the space for name. Okay, so name is going to be defined as a label, and also applicant is going to be defined as a label. So I'm just going to say. So now you have to think about what the stack would look like. Okay, from main's perspective, there's no return address because main is not called from another subroutine, so there's no return address. So we only have the local variables in this case. So the stack is going to look like this. We'll allocate in the order of the C code. In other words, we see name first, we'll reserve for name first, and then we see applicant next, we'll reserve for applicant next. So when you look at the stack, okay, name 3, name 2, okay, this is going to be somewhat repetitive. That's the last 4 bytes on the stack from the perspective of main is the local variable name, excuse me. So name as a local variable is going to occupy the last 4 bytes on the stack. And then, let's not make it 32 because that's just going to be an overkill. We'll make it 5. Just so that I don't have to, do this like 32 times. So we have applicant 4 and copy and paste, copy and paste, and then copy and paste one more time. 0, 1, 2, 3, 4. Okay, so the stack pointer is going to point to the last byte that we reserve, and we have to make this happen because the stack pointer originally is pointing past the end of the stack. So we have to do some calculations to do all of these allocations. But if based on this information, where do I find name? Where is main relative to where the stack point is pointing to? Let's count. This is SP plus 0, plus 1, plus 2, plus 3, plus 4. This is plus 5. Okay? So we'll say name as a label is defined as 5. Applicant as a label is defined as 0 because it is the last thing that we allocate from the stack. So the stack pointer really is pointing at the beginning of applicant. So that's why we label name, we define label name to be 5, and we define label applicant to be 0. Okay? But having these label definitions doesn't mean the stack pointer is already automatically adjusted to make the stack look like this. It is not done yet. So to actually do this, we have to use actual instructions to decrease the stack pointer by the total of 9 because we're reserving 9 bytes altogether. So now we have to kind of do it. Instead of using 9 decrement D, we'll use a slightly faster way to do it. Okay? Okay, that's a much faster way to say, decrement D 9 times. Are we good so far? So line 16 of the assembly code is here so that we can reserve the space for the local variables. Are we good so far? Okay. All right. So now comes the initialization part, okay, which is going to be a little bit tedious. So what we need to do is to go to name, okay, so we'll, just in the wrong window. So we just do a LDIA with name, add AD, so that name is now the address of the array name. Is that okay? And that's all I need for now. I need to store the character T into it. I think I did this yesterday, and I think the ASCII code of that is 54. This is the ASCII code of uppercase T. Store that to whatever A is pointing to. Increment A, move on to the next byte. LDIB with lowercase a. Lowercase a is 97. Okay, this is the ASCII code of lowercase a. Store to whatever register A is pointing to. Increment A again, because we need to go to the third location. This time we're dealing with K. So K is 107. Do another store. And now we have the Null Terminator. So the Null Terminator has an ASCII code of 0. Oh, I forgot to increment first. There we go. So this is the ASCII code of the null character. Store that. And now we're all done. Okay. So this is how we do, it's a long way to initialize name as a local variable to TAK as a string. Okay, if you do this in C code, it's like super duper easy, but to do it in assembly code, a little tedious. Are we good so far with all of this? Yes? Okay. All right, so this is the initialization. So now we can actually move on to the call to string copy. We are pushing the address of name, and also we are pushing the address of applicant. Now, this is the confusing part if you're kind of relatively new to C, because you would think that we should have the address of in front of both of the arrays. Because without the ampersand, we're pushing array name and we're pushing array applicant, to become the parameters. But we are only really pushing the address of the arrays onto the stack. This is where it gets a little bit interesting. Both forms are acceptable to most C compilers. A C compiler would actually take this and say, yep, it's okay. And if you remove the ampersand, it will also be okay. Because in C and C++, you cannot pass an array by value. It is simply not supported. So whenever you pass an array, it is always passing the address of the array. So taking the address off is redundant. It is not needed. But I believe this is not most C compilers won't complain about it. Okay.
It won't complain about it, but if you do that, won't it take the address of the pointer, and when you dereference it, it'll give you the pointer itself?
So that is the tricky part, because name and applicant in this case, they're not pointers, they're actually arrays. So if you have const char asterisk name instead of name in brackets, with stuff after that, then it would change the meaning. This is the fantastic part of C and C++, where arrays and pointers are kind of the same thing, but really not the same thing. Now, I just want to confirm, because I don't want to claim something and it turns out to be false. Okay, so I'm going to confirm that. So we'll say this is string copy.c, and then we go to the command line, go to the temp folder, which I'm already in. So gcc-c-o, string copy.c, and it complains about, oh, that's because note, expect char pointer, but argument is of type char pointer 5. It is not considered an error, it is only considered a warning. So if you ignore the warnings, the program actually did compile. Now it's also complaining because I'm using the same name. If I say this is tax, string copy, it would probably change the error message. There we go.
Because it already has a function.
Yeah, it already has a function, and GCC is pretty smart about built-in functions. Okay, it still complains about the same thing, but it is only noted as a warning. It is not an error. So so this is something that you have to pay attention to, because I don't know how many of you pay attention to warnings. You should always pay attention to warnings.
Read the warning and then run it anyway to see if it matters.
You can, we can run it, sure. So we can do a Gdb String Copy. So let's just say that I'm overconfident, and we'll put a breakpoint when it's all done. Okay, run the program, it's all done. We can now print what name has. Okay, tag, that's expected. Print applicant. It is also tag.
It has 3 zeros.
It's a \30 because the yes, because the actual last terminator is not shown here, because it is interpreting tag as an array of 5 bytes, and the null terminator, the actual null terminator at the very end, is not printed. So it does work. It's just that there's the extra warning and say that the ampersand does not seem to make sense. Okay, so getting back to the C code and also back to the assembly code. Okay, so we got everything done here, and we just need to push the arguments on the stack now. So the main program is right here. Okay, so to do that, okay, we do a LDIA with name, and do add AD. Okay, so this becomes the address of name, which is all we need. We don't need, and then we push it on the stack, decrement D, stda. So this is for pushing name on the stack. And then we do something like that. Okay, push LDIA with applicant 1 plus. Same kind of problem, because the argument of name is already pushed on the stack. Therefore, the stack pointer is now 1 lower than what it was. And then I have to change the offset to everything because the stack pointer is now pointing to 1 byte below where the entry point of where it was pointing to at the entry point of the subroutine. Okay, so add AD, decrement D, store to D, whatever A has. Okay, so this is for pushing applicant. It is not pushing applicant plus 1. It is just pushing the local variable applicant on the stack. Is that okay? All right. Then what do? Push the return address. Okay, so we do a decrement D, LDI A15 plus, STDA, and then do an unconditional branch to the subroutine that we're calling, which is string copy. When it returns, we have to increment D twice to get rid of the arguments that are pushed on the stack. And then we can technically halt at this point, but the stack is not balanced. In other words, the local variables are still existing on the stack right now, which is not a good thing. Okay, so we should deallocate all the local variables as well. So that means we have to do an LDIA with the number of bytes to deallocate, which is 9. And then we do an add this time. We add A to D to increase the stack pointer by 9, so it should get back to 0 at this point. And then we get to the halt instruction. The program should stop at that point. So do we have any questions about the implementation of the C code in assembly? No? This is all okay? All right. So we'll run the program in 2 ways, okay? So we'll run the program in interactively, just so that we can look at the RAM content and see that the string is in fact copied. And then we'll run it again using the command line interface so that we can use the trace analyzer to look at the actual process of running that program. Okay, so we'll do it in both fashion. So Control A, Control C, go back to one of the browser windows. I cannot remember which one. This is the trace analyzer. We can keep that one around because it is useful later on. There we go.
You need tab sorter for your desktop too.
Yes. Or I can get a computer with less RAM. All right, so we get to the source tab first, okay? And the other program that I was using was actually shorter than this one, so just pasting this new program should be fine. And we'll wait for the assembler to do all of his magic. Check and make sure that there are no errors. Okay, so it all looks good. And then we get to RAM file. File, download as CSV. And this one is string copy. There we go. All right, so we got the code ready to run. Go back to the command line. And then we can use Logisim. Oops. We'll pick the one that has that is using the GUI version. So that's going to be 2027. There we go. And we'll have to resize it. There we go. Right click on RAM and load the image, which is temp string copy.csv. Okay, program is already loaded here, and then we can just run it. I'm fairly confident that it works, okay, but it wouldn't be the first time that I be a little bit overconfident. So we'll see. We'll enable ticking, keeps going, and it's all done. All right, we'll stop the ticking, which is Control K. All right. Then we look into the RAM. Okay, we edit content, look into RAM, and we ask, is tag copied? Okay, let's check. This is name. Okay, name is an array of only 4 bytes, initialized. So we can see 36, 61, 6b. Those are the ASCII code of uppercase t, lowercase a, and lowercase k, and the null terminator. Exactly the way that I intended to initialize the name as a local variable. Where is applicant? Applicant has 5 bytes. That is below name. This is the beginning point of name. So if you count 5 bytes backwards, 1, 2, 3, 4, 5, this is the beginning of applicant. And when you look at applicant, the first byte of applicant, the second byte of applicant, the third byte of applicant, and also the fourth byte of applicant, they all match name. So the string copy actually seemed to work. Okay. So the other thing, the stack was used quite a bit, okay, during the process. So we're not too concerned about what is on the stack and how it got used, because that is the job of the trace analyzer. But one thing I do want to check is whether the stack pointer is 0, because it is supposed to be balanced, which means it goes back to the initial value of 0. So we go into, well, actually we don't have to do that anymore, because register D is also brought out as an output pin. So we can see register D is in fact 0, 0. So the stack pointer is fully balanced. So I have a fair amount of confidence that the program did work the way it's supposed to. But this is just for verification. In other words, the whole program is already working, and we are just doing a fairly superficial examination to make sure that things did work the way it's supposed to. But it does not really quite explain what is going on while the program is running. Okay, so I'm going to run the program again, this time without the use of the GUI version, and we'll run it on the command line this time. So to run it on the command line, I'm going to copy and paste this command and change only the name of the CSV. So it's string copy this time instead of string length. So if you're curious about string length, you can check out the videos for the Tuesday, Thursday class. So it's good to look at another example program if you have the time to do it. Okay. So we're gonna change this to string copy, and I forgot the J. Okay, there we go. When I copied, I did a very sloppy job and did not include the J. There we go. All right, so it's all done. So now we go to the trace analyzer. I know the use of the trace analyzer may seem a little bit cumbersome, but it is actually a fairly useful tool. So this is a trace analyzer. I have another window in the other browser. So we can do an import, go to upload, and specify log.tsv. And then make sure that we select replace current sheet.
So that's on analysis?
Huh?
Don't you want sheet 1?
Ah, yes.
Okay.
Thank you.
Yeah.
Because otherwise I would end up destroying, the analysis tab, and I don't have a copy either. I would have asked one of you to give me a copy back.
You can restore previous version.
Exactly. That's one really nice thing about Google Documents and Google drive in general is you can go back. Even if you have a shared document, let's say you're co-authoring a paper with somebody else, and that person, decided to sabotage and just delete everything, you can still kind of get back in and find out who did what at what time, which is good.
Press a button that says remove previous versions.
When you share, I think you can share at different levels too. Yep. So we can upload, and then we go to log.tsv. Okay. Replace current sheet tab and say no here. And then we wait for the spreadsheet to get all this magic done. Now, this trace analyzer is in some way, similar to what we call a logic analyzer. How many people know what is a logic analyzer? Nope. Okay. Nope. A logic analyzer is an actual device, relatively expensive, and I can show you what it looks like. I mean, a lot of this stuff, you might think, it is irrelevant to what you're learning in this class, but the knowledge, can come in handy later on in, let's say, a job interview. Just knowing what a logic analyzer is already gonna give you an advantage over some of the other applicants when you're applying for a job. It is very expensive. So a logic analyzer, looks kind of like an oscilloscope. Huh?
Looks like a microwave.
Yeah. This is a benchtop logic analyzer. So let's click on this one. Okay, this is actually a very inexpensive one. Back in the time when I was working for an embedded system company, a logic analyzer would cost about $8,000 to $10,000 used, and we are talking about 1990 at the time. So 30 years ago, okay, one of these things will cost $8,000 in the currency of 1990. That's how expensive these things can be. And let me see, do they have a? Oh, that's great. That's just not useful. So anyway, the actual web page.
I'm sure they sell on Amazon.
You mean like this? It's going to be fuzzy. It just doesn't have the resolution. It really just doesn't. But anyway, what it really is you can plug in what they call pods, 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 and the pods, each one is has a lot of wires coming out of it, okay? And then those wires will connect to sockets, okay, of processors. So what a logic analyzer can do is it can monitor, all the wires coming out of a processor. Okay, so if you think about Logisim, okay, all of those wires going everywhere, a logic analyzer can attach to all of those wires that is coming out of a processor, so it can actually understand what is going on between ROM, RAM, and also the processor itself. By monitoring that traffic and understanding what architecture is being monitored, it can go back and give you what we see as the trace analyzer. So it can actually tell you, oh, the processor is now executing this instruction, and in the process of executing that instruction, it is going to this place, grab that content from memory, and go back to the processor. Now, if the process architecture is also known, it would also know which register is getting updated and what the current value of the register is going to be, and so on and so forth. So this kind of tool is the only way to debug an embedded application when the embedded application does not support any other debugging tool. So it's either using this or you use two LEDs to debug a program. And the program itself is written in assembly language and thousands of lines. So it's your pick, okay? Is it worth the time? Is it worth the money? Like it's only like $3,000 now. I mean, by comparison, it's actually pretty inexpensive. Yep. So back in my days, debugging is mostly a few LEDs and a few wires and a voltmeter. And using that, you have to debug thousands of lines in code that is written all in assembly. And on top of that, the hardware engine you're debugging not only code in software, but the platform, the actual hardware board itself, has not been debugged. So the hardware engineer or the people who design the circuit board will drop a circuit board they just got soldered on, got all the components soldered on, assuming everything is done right on the hardware, on the circuit board. They drop it on my lab and say, "Tech, make it go." And more than once, I have found problems with the circuit board itself. So it's not because of my code being wrong that it's not working. Certain other things on the circuit board was not correctly implemented. So that's how I learned how to read schematics of circuit boards, because I go like, well, assuming the circuit board is done right, this really, it should be at least be able to light up that LED over there. Nope. And then I have to examine PAL equations. Do you guys know, how many people know what is a PAL, P-A-L, in the context of electronics? Okay, it's a programmable array of logic. So that's how they do some of the glue logic. Things that we see as multiplexers and demultiplexers, and the random gates that are sprinkled around. A lot of those can be done in PALs. So sometimes the hardware engineer would use the wrong equation in the PALs, and the board just doesn't work because the multiplexer is sending the bus to some place that is not supposed to go. So fun time, back in the 90s. Okay. Now I'm being a little bit nostalgic. Maybe we should make that a homework assignment. Use a logic analyzer to debug a program. Well, this is exactly what we're doing, okay? Now, how do you make use of a trace like this, okay? That becomes the next question, because if it's not for the lab that you're doing for right now, which is the swap subroutine, you might find this to be very useful in the next homework assignment, which is the implementation of Fibonacci using assembly code, okay? So how do you debug a program? All right, so that's the reason why I have a kind of split screen here, because when you're debugging a program, it really helps to have one screen on either the assemble or the assemble tab is really helpful already, because in column A it shows you the code, and then you can also examine what is the actual opcode and what is the constant being loaded into the instructions. So the first thing we're going to do, because I think we talked about this a little bit earlier, is what is this doing? Okay, applicant 1 plus. So applicant 1 plus is loading a 0, 1 into the register. And if you remember, we have name as the first local variable, so it has a higher location, and then we have applicant being the second one. So applicant as a label is defined to be 0, but applicant 1 plus is 1. So we are actually loading the result of evaluating the expression into register A. So is that answering your question earlier?
Yeah.
Okay, all right. All right, so when you're debugging a program, okay, most of the time you want to, you don't want to read the entire trace because it can get very lengthy. So in this particular case, we are looking at string copy. So we look into string copy. And this is the entry point of string copy, which is at location 46, that's decimal, and 2E is in hexadecimal, okay? So what you do is you look at 2E, and then you switch to the trace analyzer, and you kind of look, search until, execute at, which is, your program counter, is that location. So you look for this to change to 2E, which is right here. So this is the first, this marks the first invocation of string copy. Okay? Now, at this point, what is on the stack? It doesn't show you, right? So what you need to do if you want to find out what is on the stack at this point is to go back a little bit. And then you pay attention to the RAM write column, which is column C. So this tells you that F4 is getting the value of 28, which is the return address. F5 is getting the value of F7, which should be the first argument, which is what? Applicant, okay? So this is supposed to be the address of applicant, and F6 is getting FC, which is supposed to be the address of name. Those are the things that should be on the stack at the entry point of the first invocation of string copy. Is that okay? So according to what we know about the algorithm, it is recursive, and it has to go 4 times. There should be 4 invocations, stacked upon each other, when we execute this code. So the next thing you want to do is to look into where is my second invocation. This is the first one. So to look for the second one, you can just kind of scan, or you can use the spreadsheet's own function to search for 2e in a particular column. Okay, so here's 2e again. So in this case, this is the content on the stack. F1, location F1 has 4F, which is the return address back to string copy itself, because this is already a recursive call. This is the second invocation, which is from string copy itself. And then we can see this is the first argument. It is F8, which should be 1 byte past the beginning of applicant, and we see the other byte is FD, which should be 1 byte past the beginning of name. Is that okay? Are we good so far? More or less? Okay. Now, what if you want to focus on, did I actually copy the bytes correctly into those locations? So now you have to think about, where am I supposed to be copying those bytes into? Okay, and having a memory map, on a piece of paper is always going to be helpful. So what we can do, okay, I'm just going to draw this on the whiteboard. So what you can do is to say, okay, location FF, FE, FD, FC. Okay, those are the last 4 bytes. That's name. That's our local variable name. We should have initialized this using TAK and null character. Okay. Then the next 5 bytes. Okay, if you count backwards 5 bytes, which is FB, FA, F9, F8. That's 1, 2, 3, 4. One more. F7. That is our applicant. Okay. So this is name. This is applicant. And they have unknown values to begin with, because that local variable was not initialized. Okay. So when you look at the trace analyzer and you say, when did we write something into the first byte of applicant, which is location F7, look for F7, star F7 equals to something in the trace analyzer. Okay? Because if you don't see anything like that, that means your algorithm probably is not doing what it is supposed to. So you can see F7 gets 36, over here. So this is telling me that 36, which is the ASCII code of uppercase T, was written to location F7, which corresponds to the first byte of applicant when we are at location 37 in the assembly code. Okay? Then you go like, but where is that? Okay? Where does it correspond to in my source code? So this is why you want to kind of keep the assembler window open. If the assemble window is a little bit too busy, which it kind of is kind of busy, you can go to source debug, which is a nice summary of stuff, okay? Because column C is the address of the instructions. So you go here, okay, you go to location 37, and you ask, what is that? Location 37 is right here. And according to the comment in the original source, that line really is supposed to implement whatever source points to is assigned to whatever destination is pointing to. And that matches the behavior of the program. It is supposed to fill in the destination byte by byte from the beginning to the end. Are we doing okay so far with this? Yes? Okay. Then let me ask you another question, okay? This one has to do with the C code itself and the logic of the program, but it is also kind of interesting from the perspective of, if you change the program to do this, what else would you be observing? So I'm going to fix it so that the compiler doesn't complain about this extra ampersand here. Okay. If I put this line somewhere else, okay, I take this line, okay, take it out and put it here, do you think the program will still be working correctly? And if it does, how would it change the trace? So we'll answer the first question first, okay? Will this implementation of string copy still work correctly? Will it copy the entire string? So how do you analyze this? Okay, you think about it from the perspective of one single call. So don't think about the nature that it is recursive. Just think about, okay, I'm the subroutine. Okay, somebody called me, and we'll just handle the non-recursive version first. Okay, the non-recursive version basically says, or the case where it is not recursive is when source is pointing to a null character. Okay, so when source is pointing to a null character, this condition will be false, right? We're not going to execute the then portion of the conditional statement. So we end up only copying the null terminator to the destination, which is good. Okay, that's the correct thing to do. Are we doing okay so far with that? Okay, what is the other case? The other case is source is not pointing to a null character. If source is not pointing to a null character, star source is going to be true. If star source is going to be true, it will call recursively first. But is that okay? Is it okay to copy the rest of the string and then copy the character that I'm? Yeah, that's fine. So the algorithm is actually also correct if you change the order of line star dest equals star source. You can move it from the beginning to the end as long as it is done. It is actually okay. But the way it will change the trace is going to be a little bit tricky, because it will end up copying the null character first, and it will copy the rest of the string backwards. It is not copying the string backwards in the sense of TAK is copied as KAT. It is copying the null terminator first, and then will copy the K, it will copy the lowercase a, and then it will copy the uppercase T. But it will still end up copying the entire string correctly. Exactly. Yep. So those are the little things that you can play with, okay, when you're trying to understand the code. Now, what if the question is, but I don't really get, recursion, I don't know exactly how many times it's going to be called and what source and destination will be when, for each function call. You can use the C version to help you understand recursion. Okay, use the source version of the C code, and then you use GDB, or if you use code blocks, you can also use GDB commands in that little box, down at when you're running the program, and you can do a backtrace BT to look at what the stack looks like. How many invocations of string copy there are on the stack, and for each invocation, it will show you what the parameters are. So you can actually understand the recursive nature of the algorithm using C and all the tools that you already know how to use in C and C++ programming before you try to write it in assembly and debug the assembly version of the same code. So those are the little things that I can recommend when you're writing your programs in assembly. Is start with the C version first, debug and understand the C version, then you translate it into assembly. Okay, and then the other thing I can also recommend is really just, don't do the recursive call. Make sure it can handle the null terminating case first. Okay, in other words, you just implement this whole thing, but without line 8 being there, or comment out line 8, so that it will terminate correctly when it encounters the null terminator. Okay, just make sure you can handle that base case. Then you put in line 8, and then give it a string of only one character besides the null terminator to make sure they can handle just one recursive call. Okay, use test cases that make sense. Okay, test the base cases first, and then test the more complex cases. The swap subroutine doesn't have a recursive nature, so you don't have to kind of plan out how to deal with the swap subroutine, but it does help. Okay, if you implement the swap subroutine first in C, go through the C debugger, find out what is going on in the C program as it executes, then implement the whole thing in assembly. So are we doing okay so far? All right. We are running out of time, and I know you guys have turkey to prepare for tomorrow. I don't. So I'm going to stop the lecture at this point. There's no new lab for today. So if you want to continue to work on the swap subroutine in the lab, that's good. I will be there. On the other hand, if you say, I am done with that program, or I think I got enough time on my own to do it, well, go home and, get your turkey done.
See you next week.
Yep.
Happy Thanksgiving.
Yep. Happy Thanksgiving to you.
What's the passcode for this lab?
For which lab?
For the subroutine lab?
Swap.
Yep. Swap. Yep.